Okay, thank you. So my talk is about Veneziano amplitude and QCD. Well, this is the Veneziano amplitude from 1968. And essentially it marks the birth of string theory. And at the time it led to a lot of excitement. And part of it is because, well, it has lots of positive features. And more importantly, if we look at the pose in the amplitude, we see that there are linear radial trajectories of this form, so it's, and the daughter trajectories, so it's very appealing. So it was pre-QCD and it led to excitement, but on the other end, we know that this amplitude cannot be the correct answer because it has several bad properties. For example, the UV behavior. If we take both s and t to infinity with s over t fixed, we see that the amplitude decays as exponential with s or t, and that is not what we see in nature. That's not what we get in QCD. That corresponds to the perturbative regime of QCD, and we know that we get a power-like and not an exponential decay in this regime. So then the question that I asked myself when I first read Green-Schwarz-Witten. So it looks a bit like QCD. It looks like something close, but it is not. So what is the relation between this Veneziano amplitude and QCD? And so we know that it's not real QCD. So the question maybe, what I mean is that, is there a limit of QCD where Meson scattering is described by the Veneziano amplitude? So this is the question that I want to answer today. The answer more or less is no. I mean, it's not really a limit, but we will see that there is something that we can do to QCD, and then we will obtain the Veneziano amplitude. So, well, we have a clue. So the first thing that we should do, we should take the large NC limit. And why? Because we have a clue. We know the string amplitude, and it has the topology of the disk. And that, now we know a posteriori, corresponds to large N. So we will take, the first thing to do is the large N limit, keeping the top coupling fixed, the number of flavor fixed. So what we calculate is a 4-point function, let's say, of Meson operators, of these operators, and that indeed has the topology of a disk. There are no holes, there are no handles, so that's what we will take. And now what I want to do is something which is close to a derivation of the Veneziano amplitude from large N QCD. So let's see what we do. So I start with some technical stuff. I take the partition function of QCD, and I'm looking at the fermionic determinant. So that's the fermionic determinant. And what I will do, I want to take the large N limit, so I want to consider QCD in the Toft limit. So what I do, I will use something called wordline formalism. So this gamma that I wrote here, this gamma, I will write it in the wordline formalism. It's the logarithm of the fermionic determinant. And I will also expand the exponent, because in the large NC limit, it's an expansion actually in an f over NC. So let's see. So the explicit form of gamma is that. There are wordsheet or wordline bosons and fermions. It's quite complicated, but essentially we should think about it as sum over Wilson loops. We have Wilson loops here. And it is similar to the hopping expansion of lattice QCD, and I will comment about that later. So I use that, and then if I just write the partition function using the wordline formalism, and I expand the exponent, so I take only the first contribution, the 1 plus this gamma that corresponds to a fermionic loop, then I get the following expression for the scattering amplitude. So in the largency limit of QCD, I can write the scattering amplitude of 4 mesons in the following way. So what do we have here? We have a sum over all possible Wilson loops of all sizes and shapes of all lengths. These are the T, capital T is the length. And for each Wilson loop, I'm calculating the expectation value in the pure Young-Mills vacuum. So that's an expression for the scattering amplitude in the largency limit. So, yeah. Yeah, it's like, if you wish, largency limit, think about it as quenching. It's like quenching. Okay?
There's no, the gamma matrix structure that you put for the mesons.
The mesons, I took scalar. Scalars for simplicity. It doesn't matter. I can do vector mesons and I can do other things. But think about scattering of 4 pions. All right? And it doesn't matter for this, for what I will discuss, not so much about scalars or pseudo-scalars. So that's it. That's the expression. And the reason I'm using this expression, so I'm claiming that in order to calculate the scattering amplitude, I have to sum over all possible Wilson loops that pass through the points x1, x2, x3, x4. Okay? The reason that I'm using this wordline formalism and this Wilson loops is that we know how to calculate Wilson loops in string theory using holography. So that's my way to link field theory with string theory. I can map the problem in field theory to a problem in string theory. So that's why I'm using it. The prescription of Maldacena to calculate an expectation value of a Wilson loop is to take a minimal surface that ends on the boundary of the space. And now I will have to select all possible such string worldsheets that pass through the points x1, x2, x3, x4. So this is the, let's say, 4D boundary. These are the 4 points. So a typical configuration looks like that. And if I have a confining background, so that's the holographic coordinate, I will have some cutoff. And the string worldsheet sits on the infrared cutoff, or in part of it, if it is large enough. Okay? We will see what I need to do in order to calculate it in QCD. I need to calculate the Wilson loops in the Young-Mills vacuum, in the pure Young-Mills vacuum, right? So what I will need, and we'll see, a background that is dual to pure Young-Mills theorem. All right. Okay. I'll reach it. So that's what I need to do. So the expression is the following. In the field theory side, I need to sum over all possible Wilson loops, and that I claim, or I propose, is equivalent, that's ADS-CFT, this statement, to a sum, let's say, of the Polyakov action of the string, or actually I will need a superstring, of all string worldsheets that terminate on the ADS boundary and pass through the points x1, x2, x3, x4. Okay? So it's kind of general, this relation, but since I need to calculate the Wilson loop in the vacuum of the pure Young-Mills theory, I'll need a background, and that's encoded in the metric that describes pure Young-Mills theory. Unfortunately, we don't have such a background. So what I will do, I will use Witten's model for a confining theory. The model is good enough because it captures the main things that I will need. An areal of Wilson loops, confinement, mass gap. So if we use Witten's model, we get all these features, and that's what is essential for the discussion. This is the Witten's model. There is a metric. The metric is given by by that. And then this function has a metric singularity at u equals ukk. And therefore, if we calculate the expectation value of Wilson loops using Witten's model, we get an area law with this string tension. So going back to these worksheets, what I expect is this: if these 4 points are well separated, the string worksheet will be mostly on the infrared cutoff, and I will get an area law. And that's what we expect in QCD, right? Large string worksheets, large contours in field theory, in the pure Meson theory, they exhibit an area law. So now I want to calculate the right-hand side. So that's what I need to do. I have a metric, and it's quite complicated sigma model. It's highly nonlinear sigma model. So I will make some simplifications by ignoring some things which I consider as artifacts. So Witten's model is type 2a, so it's 10 dimensions. 5 dimensions are like compact directions which are more of an artifact than a feature of the Yang-Mills theory. So I will ignore them. So I'll claim that it's mostly from the 4 directions, and the contribution comes from the 4 dimensions and the holographic coordinate. So this is what I want to calculate. If I could calculate this sigma model with this GUU, which is rather complicated, if I could do that with the GUU and the GMU here, which also is U-dependent, if I could do that, I would be able to calculate the scattering amplitude of mesons in large N QCD. However, that's a complicated task because of this, because from the point of view of the sigma model, it's a non-trivial sigma model. So let me do the following thing. Let's assume that the string worksheets are large. So then, as I said, the strings will rest on the cutoff, and most of the contribution will come from the cutoff, from the infrared cutoff. So let's make an approximation which is not justified. It's not a justified approximation, that this path integral is dominated by u equals ukk. So I insert a delta function into this path integral, and let's see what happens. So this is not a justified approximation, but as we shall see, that will lead to the Veneziano amplitude. So I'm doing that, and then I can approximate this path integral by the 4-dimensional flat model. So G hat is this for the flat, and then that's a trivial calculation because it's a Gaussian integral. It's easier to calculate in Fourier space, so I need to do a Fourier transform. In string theory, what I really need to do is to insert vertex operators. So let me insert vertex operators. And then the amplitude in momenta space is given by this expression. I can do that, it's flat space. Flat space string theory gives the Veneziano amplitude. So now we learn the lesson. If we do large N QCD, in order to obtain the Veneziano amplitude, except we should make an approximation where all the string worldsheets sit on this cutoff, or we simply take flat space string theory. That corresponds to an area law. So the approximation that I made is that I said all Wilson loops give an area law. And we know that this does not hold in QCD. In real QCD, small Wilson loops don't have an area law. In the perturbative regime, we don't get an area law, only large Wilson loops. So the physics of what I argue is of the Veneziano amplitude is that we kind of focus on the infrared, on confinement. We approximate everything by an area law. And that's the physics of the Veneziano amplitude. A comment about the lattice strong coupling expansion and the hopping expansion, since there are many people from the lattice community here. If we start with the lattice action, we do the hopping expansion, and then the strong coupling expansion, we get an area law. So we get essentially this expression. If we take 4 operator, Mesonic operators of, let's say, scalar theory, we'll get exactly the same expression as I had in my continuum theory. I always get an area law to the leading order in the strong coupling expansion. So if I calculate scattering amplitude in positions in coordinate space on the lattice in the framework of the strong coupling expansion, and then I'll compare it to the Veneziano amplitude. Let's say take the Veneziano amplitude and do the Fourier transform to coordinate space, I will get the same expression. So it tells us that the physics of the hopping, leading order in low hopping and strong coupling expansion is the same as flat space string theory. It's dual. We can discuss it later. So now let me move to what can I do in order to improve this approximation? So I started with a crude approximation where everything is flat space. I obtained the Veneziano amplitude. Now we understand that the Veneziano amplitude is zooming into the infrared. But QCD contains asymptotic freedom. It contains all the interesting RG flow from the UV to the infrared. So can we incorporate some effects due to the UV? So what I will do, I'll do that. I want to improve a bit upon what I did. So instead of just having flat space string theory, I'm going back to the holographic model where I have this U coordinate, and I will incorporate fluctuations in this holographic coordinate. So now the worksheet is not rigid on the cutoff, but it can, I will allow some fluctuations. So instead of, I will omit this delta function that I put, but I still kind of zoom near UKK using a cross-calc transformation. And to leading order, what I get is 4D flat, this U coordinate, and then an interaction term between 4D and the additional coordinate of this form. And the coupling is 1 over the infrared cutoff. So when I push the infrared to the UV, and lambda goes to 0, I'm back to the previous case. But now I will allow some small u, some perturbation. So I need to incorporate, this is a non-trivial sigma model because I have like 4D, another coordinate, and then the interaction between them. This is like, well, it's a u squared, x squared, it's like 5 to the 4th theory. So let's see what I'll get. So I want to calculate the propagator on the worldsheet. That's the trivial level that gives the Veneziano amplitude. That there is an uninteresting one loop kind of diagram that doesn't do much. It's not interesting, and it starts getting interesting at 2 loops. So I want to calculate this 2-loop diagram. It's the correction to the propagator, and it will lead to a deviation from the Veneziano amplitude. And let's see. Oops. So this is the diagram. It's a rather complicated expression, but it's doable, and that's the result of the integral. So now equipped with this result, I can substitute it back and calculate the scattering amplitude in the presence of this alpha prime correction. That's an alpha prime correction, perturbative on the worldsheet. I do that, And now I have a deviation, so the original Veneziano amplitude is the beta function, b of s and t. I can write the correction in this form. So this is the correction to the Veneziano amplitude. And let's focus on the Begge regime, where string theory is successful. However, I'll get small deviations that perhaps I can compare to what we know from the experiment or from QCD. So what we get is the beta function is s to the t, which is the exponent of t log s. Then the corrected expression takes the following form. So instead of having exponent of t log s, I have a correction with lambda squared log cube s. I can write it in this way. So we can think about this correction as a deviation from the linearity of the Regge trajectory in this regime. So what we know is that one of the results of the Veneziano amplitude is that Regge trajectories are perfectly linear, but they cannot be perfectly linear. Perfectly linear we obtain when Wilson loops exhibit area law to all sizes, including tiny Wilson loops. So there should be a deviation from the linearity of the Regge trajectories for small s. And indeed, in this regime, I should get some correction. So alpha of s takes the form of s to this power, which should be a small deviation. And if we plot alpha of s as a function of s, we see that indeed instead of linear, we get something like a deviation from the linear Regge trajectory due to the effect of this fluctuation, this two-loop diagram that I calculated. So, so that's the result. That's the main thing that we obtain using this correction. That seems to be compatible with both data about Regge trajectories. So when you do extrapolations for small s, that's what there seems to be, that corresponds to, seems to be found in the data. Also other approaches in holography where people take into account the spectrum of mesons in, let's say, Sakai Sugimoto, and if you take into account the curvature, you get some deviation for small masses, and you see something that looks like that. Okay. So conclusions. So what I did, I started by showing that the Meson scattering amplitude can be expressed as a sum over all possible Wilson loops. As I said, that's very similar to the hopping expansion on the lattice. Then, using holography, I mapped this sum over all possible Wilson loops that pass through the scattering points to a sum over string worldsheets. Then I did two things. First, I did some unjustified and crude approximation where I ignored some directions, but most importantly, I also approximated the fifth holographic coordinate, which we know it's important, by I inserted a delta function. That's also similar, like it's as if I took the infrared cutoff to the UV cutoff. So you kind of make the space flat by pushing your infrared scale to the UV scale. It's something that we will never do in QCD. In QCD is about RG flow, and we identify, let's say, lambda QCD with a UV cutoff is a disaster. But if you do that, you get simple Gaussian integration, and that gives the Veneziano amplitude. So I think the essence of the conclusion from that is that Veneziano amplitude, well, we know that it's equivalent to flat space string theory, but it means confinement. It means zooming into the infrared of QCD and ignoring asymptotic freedom, etc. Well, we know that because we know that the amplitude doesn't work well in the UV regime. But in terms of the string description, is like zooming in the cutoff, the infrared cutoff of space. I tried to improve it, and to do that, I incorporated some interaction between the 4D coordinate and the additional holographic coordinate U. And I carried out some perturbative calculation to two loops, and that gives deviation from linearity of the radial trajectories. Thank you.
We have time for questions. Yeah.
What took you so long?
Well,
I was sure that you will ask me questions. Thanks.
go back to the appointment. Hello? Is it on? Okay. Go back to your Reggie.
Who?
What? You can't hear me? Hello? 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 Can you hear me?
Yeah, it's okay.
Be very close. Okay. All right. I'll go back. Yeah. I don't understand your Reggie formula, the correction, the last one, the correction.
The correction.
Yeah, I mean,
a
Reggie pole is S to a function of T.
So
that's not a function of T. Are you trying to get alpha of T or alpha of S?
No. So first of all, it's not that I wanted to correct alpha of S. What I wanted is to see a correction to the amplitude. So what I did is not a correction to the...
You're right, but then you translated it into a pole, and that's not a Reggie pole.
No. So wait. So what I really did is that. That's what I did.
Yeah, but that is not a pole in the J plane.
Right. I didn't claim that.
So, but then you had a...
But what I wanted to say is that I can write that as some alpha of S to the power of T. Right? I can just write this.
Why?
Think about, we have some expression to the power of T. So that's what I'm doing. I'm kind of trying to incorporate it.
I guess we can discuss that. It seems very strange to identify. But anyway, I have another sort of more question, suggestion / whatever.
Okay.
We know that, I think we know, the glue ball calculations show that this super Yang-Mills has the quantum numbers that give the low mass glue balls. So you have to have a superstring-like degrees of freedom. I think we also know in flat space that the Navier-Schwarz theory is much closer to the spectrum of QCD. It has pions and rows and so on. It's really very good, actually, better than people think.
Right.
So I would think that your first approximation close to the infrared would be more like a superstring.
Right.
And I would say it would not be alpha prime equal to 0. The low mass spectrum is all infrared. I mean, in fact, the least correction should be in the low mass spectrum, and you should be able to go up the trajectory, and that's very well accounted for by the Navier-Schwarz string. I mean, remarkably so.
Okay.
So I agree that there's certainly corrections when you get to the ultraviolet, but the major corrections are when you go into the deep wide angle, and then we know that you have to get scaling and power counting, right? So I'd actually expect the corrections to not be to the right as you go up through the spectrum, where we actually know that the Veneziano, or actually the Navier-Schwarz algorithm, is extremely good.
Right. So
But actually into deep and elastic and really UV physics.
Right. So yeah, let me comment. So actually, Witten's model is in type 2A. So I mapped the problem to a problem in type 2A string theory, right? But then what I did, just to start with something, I first of all omitted the extra directions apart from the full +1.
Yes,
I think that's reasonable to do.
No, that's right.
Then I do agree that a better thing is to do a superstring.
Yeah, in
and
fact,
for several reasons.
Yeah.
Several reasons. First of all, we don't want the tachyon. So if I want to go beyond Veneziano amplitude, so I need the superstring. I need better vertex operators.
Yes. No, but I was trying to say there's more evidence than that. If you take the whole low glue ball mass spectrum, 10 or 20 states, they really fit QCD with the truncation that you made, but not dropping the bosonic fields in the super Yang-Mills theory. Those are just as important. So if you go back to if you go back to a Yang-Mills theory without supersymmetry at all, you wouldn't get anything like the red spectrum. And you get a very good spectrum if you keep in other words, you need the Raman field, you need that whole multiplet, and then it's extremely good. Right. So I think you don't want to drop that part of the supersymmetric.
I think that...
And that's much more important, I think, in the low mass spectrum. Anyway, that's
but for the scattering, just to calculate the scattering, we can discuss it, but I don't think that that's more important.
Anyway, we'll discuss it.
Okay.
More questions? I have a comment. Anyway, from unitarity, you know that the trajectory cannot be linear.
Right, right. Yeah.
So is your correction going in the right direction?
Yes, I checked it.
Yeah. Hello. Yeah. So this is maybe a question/comment. So there is this recent work in the last 2 years by various people, including Simon Keron-Huart and Zohar Komorgodsky,
right,
and Veneziano, Yanklowicz, and after that, and so on. So where they try to look at like things like large QCD and in some unphysical like analytically continued region, you can argue that it should have a Veneziano kind of amplitude. But
that's in a different.
So are you arguing that like are you arguing something stronger or something weaker?
No, I'm arguing something weaker.
Okay.
All I wanted to do is no. So first of all, their results are universal. My results are more just a small correction in certain place due to kind of worldsheet corrections, and there are other reasons for corrections. So I'm just identified one possible source for correction, and I identified where I think it should affect, and I calculated, and that's what I got. I don't claim anything universal. It's a different motivation. It's just to understand, first of all, what's the relation between Veneziano amplitude and QCD, and somehow how to improve it a bit. And that's what I did.
Okay. Sorry, I just have a second question and the last one, I promise. So there is also this work by Simeon Hellerman and various other people on trying to change the worldsheet theory, not just del x, but add other operators, right, and so on and so forth, so that, like to try to get a match with QCD spectrum, including lattice and so on and so forth. I mean, is it related to what is the relation between that work and the work that you're describing?
No, I don't think there is much relation. What I did is the following. Let's look at the sigma model that I used. This is something that you get from Witten's model. It's quite universal in the sense that if you have flat space and some holographic coordinate and you expand near the infrared cutoff, you will always get something like that, because these X are like gold stones, so there should be dx. It should contain derivatives, and the interaction, what else can it be? It's like an harmonic oscillator, so the leading will be u squared. So I claim that although I used Witten model, this is kind of a universal correction, but it's not so model dependent, but still it's just one correction. So that's what I did. Which is rather complicated, by the way. The two-loop calculation was my PhD student who did it, not me.
If there are no other questions, let's thank the speaker for every nice talk.
Thank you.